My name is Chad Shearer. I'm a senior data scientist at Metis. I forgot to wear my Metis shirt tonight, but I do have one at home. So I'm going to be talking a little bit about Julia for probabilistic programming. And following me, we have 4 other speakers. We have Elliot Saba, Valentin Chulabi, I'm butchering that horribly, Eric Egel, and Jeff Bezanson. So without further ado, let's get going. So goals for my talk. We'd like to be able to flexibly express probabilistic models at a very high level. And there are lots of ways that you can do this. The goal for this talk will be to have it be very self-contained so that you'll actually see almost all of the code that's needed to do this. And we'll have Julia rewrite these in a way that a compiler can easily optimize. So our hope is that this should be reasonably high performance. So here's a motivating example if you haven't seen anything with probabilistic programming. There are lots of built-in models in a given system. Something like sklearn has lots of different models you can use. But it's at some point, it's pretty common to hit a wall where, well, there's not really a model in my library of models that is exactly what I want it to do. And so we need to sort of sometimes express something custom. So here's an example. This is just some data with one extreme outlier. So maybe we could just get rid of that. But maybe we know that, no, that really is a valid data point, and I'd like to model this somehow accurately. So the blue line is if I do just the standard ordinary least squares, and the assumption there is that the errors have a Gaussian distribution, so that this point has the effect of pulling it really far out of line. So we use a t-distribution instead for the errors, which is maybe not something built in, but something that we can express, then that helps quite a bit. Then we get a nice fit, a more robust linear model. So how are we going to express this? So an idea that we'll explore tonight is having a model be just a quoted expression. So I can write something like this. It's very similar to what you would write mathematically. We have 2 different kinds of operations outside of just the normal code. This tilde we can think of as a sample operation, and then less tilde we can call that observe. We can express lots of different models in this framework. This cannot yet execute, right? We have to say, when I write sample, here's what I really mean. When I write tilde, when I write less tilde, here's what I mean. We have to give those things some kind of semantics. So these things are loosely defined, but an inference algorithm in this framework will just be something that takes some quoted code like this and turns it into code that can actually execute. So a simple thing that we can do, we can sample from the prior. So let's have val, that's going to be a dictionary that says, here's all of your values for the different variables in your model. So that's going to be a dictionary. It takes a symbol and returns something. I don't know what range my variables are in, so it could be anything. We'll wrap the body of the code that we just saw with, first we'll instantiate an empty dictionary, and then we'll have some stuff associated with the body, and then we'll return whatever those values are. So in this body part, we'll give those assignments. And the assignments we'll give them are just, well, we have some, anytime we see v tilde dist for some distribution, we'll just draw something from it. And then we have to assign the variable. Or we have to have a local v in case later on in the code we refer to v. We have to be able to have the code know what that means. And if there's something that says, I'm going to observe a value, just ignore it. Because all we're doing here is sampling from the prior distribution. Okay, so here's the implementation. I'm not going to walk through this in too much detail. At a high level, you can see this is that observe. We're just kind of ignoring it. Here is that sample. We're doing what we said. And then this is wrapping the body. All right, so how does this do? Well, when I call that macro, this is called a macro. Macro is like a function, but it considers its input not to be code that's been compiled, but just as an AST, an abstract syntax tree. So it takes this code and just considers it to be an expression. And then the thing it generates is new code, and this is actually evaluated when we call the macro. So when we do this, we get a function like this. It takes some data, and when I pass it an empty tuple that just says, okay, please now execute the function, it's going to, here, the code that we get from this is pretty short. And there's a little bit of extraneous stuff, like this for loop effectively doesn't do anything. So the hope in this case is that the compiler will recognize that and hopefully get rid of it. And I haven't measured whether it really is empty, but it executes pretty quickly. It takes 265 nanoseconds. In the example, we get, okay, alpha is negative 255, and beta is 2.17 something. So hopefully this is clear what's going on here.
Are we going to see later on whether or not the compiler ignored those few lines that didn't do anything?
No. We can, with a couple extra steps, we can pick apart whether it does. But yeah, I'm trying to keep pretty high level. This is just a, excuse me, very quick overview of some different approaches. I won't even show you
the compiler generally will do things like that, though. Generally will remove it.
Okay.
So, importance sampling. The idea for importance sampling is we do the same thing as before, sample from the prior, but now each of our samples is also going to have a weight. So we sample something from the prior and then say, okay, in our likelihood, when we do those observe functions, that's going to tell us, here's how likely that event is according to the data. Okay, so for the body now, we do the same thing as before. We have this dictionary that we initialize to just an empty dictionary. And then we can have the log weight, starts at 0. We do some stuff with the body, and then we return the log weight and the value. When we have v tilde dist, we do the same thing as before. So there's no change there. But now, when we observe some data, what we do is we're going to increment the log weight according to the log of the probability density function. Okay? And this is the distribution, and here's the data that was in fact observed. So here's the macro, looks similar to before. And again, if I say I'm going to call this macro expand macro, which takes a macro and expands it, I don't get exactly this, but I get this with some other syntactic junk that I've cleaned up here without changing the semantics. So I mean, it's, but my scrolling here is messed up. Yeah, kind of what you would expect if you were to write something like this by hand. Pretty similar. And it takes a little bit longer now, 1.7 microseconds. But you know, still, it's pretty good. And it does return the value of the log likelihood together with the dictionary of the thing that you sampled. So, importance sampling from a statistical perspective has all kinds of problems. We don't have time to get into those problems tonight. But something that is done maybe a little bit more commonly in practice that tends to work better is we can evaluate the log posterior, and then there's just all kinds of stuff we can do with that. We can maximize it to get what's called a map estimator similar to like a maximum likelihood estimator. We can also sample from that posterior distribution if we throw into something like a no U-return sampler. There's lots of stuff we can do with the posterior distribution. So the idea here is we're going to pass in a vector of the parameters, and we're going to walk down that, and we're going to track. Here's the index that I'm currently on. Those just zip through. Okay, and then we're going to wrap the body with something that does this. It's going to take this parameter vector. It's going to start the log posterior at 0, and then it's going to do some stuff with the body again, and then it's going to return that log posterior. When I have something that's sampled from a distribution, I'm going to increment j first, and then I'm going to return this quoted thing that says, V, the current sample, must be the jth entry in theta. Okay? And then I just increment the log posterior distribution. And then this one's off the screen a bit, I think. Yeah. And if I see sample, I just do the same thing, except that now I don't need to worry about looking into theta, because it's observed data, right? So if I do this, I get a macro that looks like this. And I can do the same thing as before. And it's pretty short. I mean, if I think about, okay, how would I, if I want to pass in a theta, and I want to find, okay, there's some alpha that's the first element. I'm going to evaluate what I thought the distribution for alpha was, and increment the log likelihood, or the log PDF by that, and then do the same thing for beta. Oh, and this is off the screen again a little bit. I'm not very happy with this way of making slides. Then I can go through the data and say, this is my residual for my observed value minus my predicted value. And my assumption is that my residual follows a t distribution with 3 degrees of freedom, and I increment by that. And I can evaluate this log posterior density in 1.3 microseconds, which, again, it's pretty good. If I evaluate that over a grid, then I can get a surface plot like this. And in fact, maximizing the value of the parameters over the surface is that robust fit that we saw at the beginning. More generally, we would probably, there's lots of other stuff that we could do with this. Auto differentiation. There are a few packages in Julia for automatic differentiation, with more on the way that the community is all very excited about. The no U-turn sampler is great for sampling from these things if you have the value and its gradient. And transforming things with Jacobians if I have constrained variables. Like if I say, I've got a parameter, but I know that this parameter is greater than 0. And it turns out I have to normalize things and move things around a little bit in order to correct for that. So that's all that I have. So thank you very much. Maybe, I don't want to, if we have maybe like 1 or 2 questions, if you guys have any questions.
Is that stuff in the package?
Kind of. There's a package called SOSS, SOSS.jl.
Okay.
And it's not exactly this. It's things were sort of in a working state, and then I decided to refactor, which means break it all and then fix it. So I'm halfway through that.
Okay, but that's your package?
Yes.
Okay, missed opportunity to spell it as S-A-U-C.
Better Googleability.
Yeah, that's true.
What do you recommend for the nuts sampler?
So, yeah, there is a package by Tomas Pop called Dynamic HMC. That's probably the best that I know of currently in existence. He also has one called Continuous Transformations that I think has a lot of potential for some of the constrained variables. Okay, thank you.